Alright, now let's look at an example of how they use it. So example 4.23, they want to do this integral where gamma is the unit circle oriented clockwise, so that would be our standard cosine 2 pi t and sine 2 pi t. And it says try computing. I don't want to do that right now. Now they do this partial fraction thing, okay, and so I think at this point everybody's seen partial fractions, but we'll go ahead and do it. So we'll start with this one, get to these partial fractions here, and then look at those results. So okay, let's see, where am I going? Back up here. Okay, we have this on our screencast. Alright, so here's 0, 0. We got the unit circle, and we would like to integrate over gamma here. Shoot, what the heck was that again? dz over z squared minus 2z. dz over z squared minus 2z. Alright, so the idea is that, this idea of partial fractions, so what I want to do is come down here and write 1 over z squared minus 2z, which happens to be equal to 1 over z times z minus 2, as sum a over z plus sum b over z minus 2. And theory says that we can do that, and so it's just a matter of looking for it. Now what I tend to do is I kind of think of this as, okay, my next step is that to sort of get towards something like this, I'd have to get a common denominator, and so I get a times z minus 2 plus b times z all over z times z minus 2. Okay, so as you look at this, this numerator has to be 1, and always, but we can mess with some things, right? Because if I let z equal 0, that numerator, now here is to me the fantastical thing about partial fractions, is when I let z equal 0, you see that actually makes no sense. But we're only talking about the numerators, and so I'm going to go ahead and do it, and it works. Let z equal 0, and what that yields is that minus 2a is equal to 1. Okay? And so that would say a is equal to negative 1/2. And similarly, if I let z equal 2, then the a disappears, but I would have that 2b is equal to 1, and so b equals 1/2. So looking back here, this a and b, it says that 1 over z squared minus 2z can be written as negative 1 over 2z, negative 1 over 2z, or 1/2, 1 over z, negative 1/2, 1 over z. Yeah, we'll do it that way, because I think that's what they end up writing there. So negative 1/2 times 1 over z, and then plus 1/2 times 1 over z minus 2. Okay, so now that means that my integral over gamma of dz over z squared minus 2z can be written as these two integrals. I can take minus 1/2 the integral over gamma of 1 over z dz and add to that 1/2 integral over gamma of 1 over z minus 2 dz. Now notice this one here, we're going around 0. So in that region, right, so you know, here's 0, but this is 1 over z minus 2. In this region, right, 1 over z minus 2 is holomorphic. In that whole region. And the where it wouldn't be any good, it'd be out here at 2, 0. But in here, it's totally defined everywhere, has a great derivative everywhere. And so what that means is that 1/2 the integral over gamma of dz over z minus 2 is equal to 0. Okay, so that was easy enough. Boom, that one's gone. And so now I just have to deal with minus 1/2 and the 1 over z. So I got minus 1/2 gamma 1 over z dz. But as they point out back here, this integral, they say, oh, well, we already know that over the unit circle, this integral, the dz over z, is 2 pi I. Okay, it's yeah, they mention here that this the other is C2 contractible, C or C minus 2 contractible, and so as I pointed out, you can use any points, but so we get 2 pi I for that, and so this is minus 1/2 times 2 pi I, because that's something we already knew, and so the integral itself, well, let me rewrite the whole thing. Integral over gamma dz over z squared minus 2z is equal to then minus pi I, because that is what's left here, and the other part was 0. So see, we didn't have to actually deal with any of those curves other than to kind of know where gamma was, so that we knew something about this one here. Okay, so we did need to know that it didn't contain the number 2 in it, but it did not, and so that was 0, and we get that for our solution. Okay, so that is the idea, and we are next up to Cauchy's integral formula. Okay, so we'll stop there.